back to chapter 5, actually. And let's talk about linear phase systems. Or should I say linear phase filters. So these are, what we're going to talk about next, are some impulse responses of finite domain. Okay, basically finite FIR filters. But somehow, if they have certain kind of symmetry in the time domain, then we categorize these filters into 4 types, namely type 1, type 2, type 3, and type 4. Okay, so next thing I'm going to cover is what really are these 4 different types. Okay? The Roman letter 1, 2, 3, and 4. There are 4 different types, depending on what exactly is the symmetry. Okay? And for this discussion, let me also mention that this is, in the textbook, we are back to the chapter 5, okay? Just to pick up what we missed from chapter 5. But in this section, let's look at our first example. Okay? Let's raise an example. Example, let's say if H of n represents the impulse response of a filter, of a linear system, an LTI system. And in particular, let's assume that we are only interested in systems that have real coefficients. Okay, all the samples in the impulse response are real in the time domain. Okay. Let me say not if, but assume that if all the samples are real in the time domain, then if we have a symmetry, the following symmetry in the time domain, it so happens that h of minus n equals to h of n for any n. If we assume that this impulse response is symmetric with respect to time 0, okay? For example, if we have this impulse response that is exactly symmetric left to right, okay. For example, if we have this relation, in the time domain, okay? And it turns out that this system is going to have, it's called the zero phase system. And what is that? That means it turns out that if this relation holds for all n, turns out that the frequency response is going to be real. So that's an important first result I want to share with you. If the filter has this symmetry in the time domain, it's symmetric left to right, around time 0, okay? If this happens, then it turns out that its frequency response. Its frequency response, in general, should be a complex number, actually a complex value. But for this case, if this symmetry holds, then in the frequency domain, the Fourier transform, or should I say, the Fourier transform that is the frequency response of this filter. The Fourier transform there is going to be real. Okay? And here is a simple check. Why is it real? Why is it real? And simply, let's just get back to the very definition. What is the Fourier transform given the time domain signal? The Fourier transform, discrete time Fourier transform is defined as we are going to take the evaluate the Z transform on the unit circle, right? But there are many different ways you can describe it. So n summing over all n, right? So this is simply the definition of discrete time Fourier transform. But why is it real in this case? Why is it real in this case? So let's separate this summation into three parts. The negative part, the negative time part, n equals to 0, okay? When n equals to 0, this is 1 and this is exactly h0, okay? Plus the positive n part. Now n goes from 1 to infinity h of n, e to the minus j omega n. And let's just let's just combine the two summations right here. But we can combine these two summations by a change of variable. Okay, by a change of variable, let's require n, the new variable, to be actually exactly from 1 to infinity. Okay, from 1 to infinity, and we keep this part. This part is still going to show up. But how about the other summation? The other summation runs from minus infinity to minus 1, or should I say from minus 1 to minus infinity, right? So with a simple change of variable, we should say here we have what? H of minus n, which will essentially go from minus 1 to minus infinity. And how about this part? E to the, because when you plug in n equal to minus 1 to minus infinity, here we really should have plus j omega n, right? Back here? But simply a change of variable. I will copy h0 down here, still around. Go back to the change of variable. Okay, we are going. What we have just done is to merge the two summations. Okay? After merging the two summations, then here we haven't applied the symmetry condition, right? So how may we apply the symmetry condition? Because we have assumed that h of, in our case, h of minus n is h of n, right? So we're almost there, almost there. And now still this summation is going to run from 1 to infinity. But here, this first term is h of n times that. The second term is h of n, also h of n times that. Right? So we have h of n. Now what is the sum of e to the minus j omega n and plus e to the j omega n? This thing turns out to be 2 times cosine omega n, right? And then outside we still have h0, don't forget it. So now we've come to a conclusion. Since we assume that our signal, our h of n is equal to stop, but it's filtered as real samples, okay? It is all real in the time domain, and 2 times cosine omega n is always real. And plus this sample h0 is also real. So that explains why the summation of all of them remains real for any omega. Okay? So that's a simple check. That completes our check. Okay, so the next thing, this property, okay, so if we have that symmetry around time 0, if the filter has that symmetry around time 0, then this filter, we know that the magnitude, the frequency response, the Fourier transform of this filter, the frequency response of this filter is going to be real. And that's why it has a name. Okay, this kind of system is called the zero phase system. The zero phase system. Why is it called the zero phase system? It's because if the magnitude response is real, no, I should say negative, if the frequency response is real, then the phase response, the phase is either 0 or pi, right? Depending on the sign of depending on it's positive or negative. Is that clear? You can take an example. You've already seen this example over and over, actually. So let's say, for example, the sinc function in time is symmetric around time 0, right? And therefore, we know that its Fourier transform is real. That's actually an ideal low-pass response is real, right? So we've seen this example over and over again. This is simply an example, okay? And in this example, and we talked about using a window, right? Using a window to truncate the infinitely long response, but still the symmetry remains. The symmetry is still there. And the symmetry is still there while we sacrifice in the frequency domain. Now we have, we're deviating from ideal. We keep drawing this picture that still the magnitude response remains real. I should say magnitude response. The frequency response remains real. Sometimes it goes negative, and other times it remains positive. Okay? So we say that, anyway, the phase, in this example, in this particular example, the phase is either 0 or pi, depending on the sign of the spectral value. 0 when this h is greater than 0, and pi when the phase, this actual value is less than 1 when it goes negative. Anyway, 0 or pi. Okay, everything is real. Everything is real. That's an important result. When we have symmetry, this exact symmetry in time, everything is going to be real in the frequency domain. And consequently, if the phase response is 0 or pi, when the frequency response is 0 or pi, and we know that pi is actually minus pi, doesn't matter, right? Pi and minus pi are the same thing. So if the phase response look like this, switching in between -0 and pi, for the case of our taking the low-pass design as an example, the important consequence is that I want to share with you. How about the slope? The slope remains 0 at every frequency where this function is differentiable. Let me say that again. The slope of the phase response is 0 everywhere, except at the discontinuity, okay, where the phase is not well defined. Otherwise, the slope is all 0 for all frequencies. Do we agree on that? And what does that mean? What is the slope about? What's the kind of physical interpretation of the slope of the phase response? The slope of the phase response is the group delay, right? So what does that mean? That means that the result of the design is going to have no group delay. Zero group delay at every frequency. And that's huge, okay? So the consequence, one kind of cool thing about our design, we have introduced designing a low-pass filter using any kind of window, right? Rectangular windows or other kinds of windows. But fine. What's important is that the result of our design is still going to be symmetric in time. And when we are guaranteed with symmetry in time, then it turns out that our system will have zero group delay at any frequency where the phase is well defined. Or should I say, at any frequency where the gain is not zero. So essentially, we have delayed a zero phase, or should we say zero delay, a filter with zero delay, zero group delay. Any question? Okay, so, but wait a minute, okay? But also, please note that here, the filter, strictly speaking, the filter is not causal yet. So, let's remember that strictly speaking, it doesn't like Japan. Strictly speaking, this filter is not causal yet. Because it has non-zero values for negative time, really from 0 to minus n. It still has some non-zero values. It's symmetry, of course, right? So it's left to right symmetric, but strictly speaking, we must admit, must admit that this filter is not causal yet. So remember that last time, at the beginning when we started talking about designing a filter, I said designing a filter consists of two steps, right? First is to pick the middle part, that's the second part. The second step is to move everything to the right, shift everything to the right, okay? So shifting everything to the right, now, after defining, let's say defining our new filter, h of n, to be shifting the old filter, shifting to the right. Shifting to the right means, shifting so much to the right, okay? After making this modification, by shifting everything to the right, or essentially by redefining the time zero, by redefining time zero to be zero at the boundary and to n on the right, okay? This is our new filter. The new filter is still the same shape, but only the time index is shifted to the right. So when we shift something to the right in the time domain, what happens in the frequency domain? In the frequency domain, the new frequency response differs from the old one by a factor, by a linear phase factor, right? So as a result, consequently, after this manipulation, we know that the corresponding new frequency response, denoted by h of tilde, h tilde, tilde, okay, tilde, h tilde, tilde, h tilde is going to differ from the originally found by a factor of e to the j omega n, because we shift everything to the right by n. That's a shift theorem, simply the shift theorem. So from here, kind of observations. First of all, simply by shifting everything to the right does not change the magnitude response. Right? This magnitude response remains the same, and we've talked about it. Doesn't change the magnitude response. Simply by shifting your filter to the right. The magnitude response does not change at every frequency. And secondly, the group delay. Now, the phase response, how much does the phase differ? The phase response of our new system is going to be the old one plus, actually minus omega n. Minus omega n. Minus omega n. So let me use the color green. Okay, we use the color green. So what's different here is that now we have a slope. And so on and so forth. Okay? Now the new phase response. The new phase response is going to differ from the old one by a constant slope. By a constant slope that goes downward as frequency increases. Okay? And here the gap is, there's a gap of pi, and there's a gap of pi. Wherever we have discontinuity in the old phase spectrum, we still have discontinuity in the new phase spectrum. Is that clear? This is our new phase spectrum. Constant slope, piecewise constant slope. The new phase spectrum is going to be not flat anymore, but actually it's not too bad. It is constant. It is piecewise continuous with a constant slope. Clear? And that slope, what is that slope? So we reach a conclusion actually. So should we say the new phase, the new group delay is simply going to be n. No, because we are talking about the delay. Delay has a minus sign, right? Not clear? Does everybody get it? Then after shifting everything to the right by n, now the new system has a constant group delay of n, and that is because we shift everything to the right by n, right? As a result, consequently, double checking. It's kind of like double checking, sanity check. Okay, by shifting our impulse response to the right by n, of course, we induce a constant group delay of n. Okay, and the result. Now, our result. The kind of summary. Now the result of our design in the time domain starts from time 0. It might not be 0 at the boundary, and that's fine. But anyway, we might have some kind of symmetry. Okay, I'm not drawing a very good picture. You get what I mean. So we have a symmetry or something like that. And this new response denoted by h delta, goes from time 0 to time 2n. Okay? So we have, note that now we have h of n is equal to h tilde of 2n minus n, where n is an integer. M is a natural number. Okay? N is a positive integer. Can we agree on this? This is the result of our design, okay? All right, so now I hope I've convinced you that we have an example of filter that satisfies this symmetry. It's left to right symmetry, symmetric, but not around time 0, but around time n, okay? It's symmetric around time n. And the exact relation is defined right here, okay? And this kind of filter, in general, has a property that its group delay is going to be constant. It is going to have a constant group delay for all frequencies. For all frequencies such that the frequency response is non-zero. Okay? And this kind of filters are generally, not necessarily the one we designed right there. Okay? Generally, turns out that generally when any filter, any FIR filter has this property. This kind of filter is referred to as, it's called type 1 filter. Okay, so this is one terminology I want to share with you. Anytime we have an FIR filter which starts at time 0 and ends at time 2n. starting time 0, ending time 2n. And if the filter is left to right symmetric around the middle point, around time n, then we can write down this relation, right? So this symmetry, when the filter has this symmetry, the FIR filter is called type 1. And we know that type 1 filter has a constant group related to n. Okay? So before we finish, let me just list the definition of other three types of filters. Type 2 is defined by this h of k minus n equals to h of n. But k is an odd number. Where k is an odd number. That's type 2. And type 3 has a negative sign. Okay? Type 3 is when h of k minus n is minus h of n, where k is like 2n, an even number. That's type 3. And finally, type 4, you can guess. What is type 4? Type 4 is also when h of k minus n has a negative sign, anti-symmetric case. Okay, the anti-symmetric case, where k indicates if it is odd, then this is called type 4. And so after next time, next time shall we do a review? Or people, let's do a review. Anyway, next, after the midterm, we'll talk about the subtle differences between type 2, type 3, and type 4, and type 1. And where are the cases, what are the scenarios you want to choose one of them rather than the other. Okay? And that's after the midterm. Okay? So next time we'll figure it out. Okay. Thank you for being here, and please share the word that we are going to allow you to bring in 2 sheets, 4 pages of cheat sheets. Okay? That's it for today. Thank you.